Let's take a look at the f-test in simple linear regression. In simple regression, we have one independent variable, and the f-test is comparable to the two-tailed t-test of the regression slope. In fact, the p-value of the f-test equals the p-value of the two-tailed t-test. The f-statistic is calculated from the various sums of squares and the degrees of freedom, and the p-value is based on a new probability distribution called the f-distribution. When the f-statistic is calculated, we use a ratio of two values. Each value in the ratio has its own degrees of freedom. The numerator degrees of freedom equals k, which is the number of independent variables, 1 in the case of simple regression. The denominator degrees of freedom equals n minus k minus 1. The f-distribution tends to be skewed to the right and is always positive, never negative. The null hypothesis is that the population slope, beta 1, is 0, which means there's no relationship between x and y. The alternate is beta 1 is not 0. With this f-test, we always reject the null hypothesis in the upper tail. You can open the help page for f by running $QF. The first argument in the pf function is p, the probability in one tail, df1 is the numerator degrees of freedom, and df2 is the denominator degrees of freedom. I use p of 0.05 with 1 degree of freedom in the numerator and 8 degrees of freedom in the denominator. Lower tail equals false puts 5% of the area in the upper tail. The answer is 5.32 rounded. This means 5% of the area in the f-distribution with 1 and 8 degrees of freedom is greater than 5.32. This is the critical value for the f-test. This means that the null hypothesis of no relationship is rejected if the calculated value of f is 5.32 or more. The p-value can be found with the pf function. When q equals 5.317655, with 1 and 8 degrees of freedom and lower tail is false, the area to the right of 5.317655 equals 0.05 of the area under the f-distribution. You can plot this f-distribution by defining x as a sequence of 100 numbers between 0 and 6. Plot x, df, x equals x, degrees of freedom equals 1, degree of freedom 2 equals 8, and type equals L for line, and the AB line, V equals 0, H equals 0, draws a vertical line at x equals 0 and a horizontal line at y equals 0. Here's what the f-distribution with 1 and 8 degrees of freedom looks like. I added a red line at about 5.32, the critical value of f. You can see in this case the distribution has a reverse J shape. As the degrees of freedom change, the shape changes. For example, this is an f-distribution with 5 and 20 degrees of freedom. The critical value at the 0.05 level of significance in this case equals 2.71. The sums of squares for calculating f come from the regression output. SST is the total sum of squares in the data. SSR is the sum of squares that is explained by the regression model, and SSE is the sum of squares that is unexplained by the regression model. SSR plus SSE equals SST. This is how the analysis of variance table in regression is organized. The DF column shows the degrees of freedom. Once again, k is the number of independent variables, and n is the sample size. The MS column shows the mean squares. The MSR is the mean square for regression. It's the SST divided by k. The MSE is the mean square for error. It equals SSE divided by n minus k minus 1. The f-statistic is MSR divided by MSE. The last column on the right is the p-value, and it's based on k degrees of freedom in the numerator and n minus k minus 1 degrees of freedom in the denominator. This slide uses the OLSRR package to perform the regression analysis. Line 1 loads the OLSR package. This package is not the only way to run regression, but it has some very nice regression tools. Lines 2 and 3 are used to import the TastySub1 dataset, and it's stored in an object named MyData. Line 4 uses the LM function to run the regression. By the way, LM stands for linear model. Open parenthesis y tilde x tells R that y is the dependent variable and x is the independent variable. The data equals MyData statement tells R where to find the data. The whole regression analysis is stored in an object named model. In line 5, OLS underline regress model produces a lot of regression output. In this video, we're only looking at the f-test. And this slide shows the ANOVA table. ANOVA stands for Analysis of Variance. This is a nice display of the sums of squares, the degrees of freedom, the mean squares, the f-ratio, and the column on the right that's labeled SIG is the p-value. The f-value of 122.21 is very high, and the p-value is less than 0.0000. The null hypothesis of no relationship is rejected, and so we conclude that the model is significant. That's a look at the f-test and simple linear regression. Thanks for watching, and please let me know if you have any questions.